Today we're going to go over shorthand structures, Chapter 3, limiting reagents, again that's a review, Chapter 17, equilibrium. Just so you know, the equilibrium we're going to go over is just the basics from what you remember from Chem 100. So let's start with shorthand structures. So given this structure, C4H10. So how would I draw this shorthand? Well, what you do is you get rid of all the hydrogens and you only represent the carbons by the bumps. So right here, this carbon-carbon, you represent that bond. This carbon-carbon, you represent the bond. And this carbon-carbon, you represent the bond. So what you're left with is this shorthand. So that's all you need to do. So each bump right here represents a carbon. Now you need to remember at the terminal carbons that they're going to need 3 hydrogens, and in the middle carbons they're going to need 2 hydrogens. Now if I gave you this structure, how would I draw it? Well, again, I would connect the bonds of the carbon-carbon, and here I would need to show the double bond and the oxygen. So let's draw it out. So it would look like this. You just need to remember that again, each little bump is a carbon, and you need to fill in the hydrogens accordingly. So because there is a oxygen double bond, we know we need to have a hydrogen right here. So that carbon fills its octet. Now let's look at another structure, a little bit more difficult. So let's take a look at aspirin. So this is what aspirin looks like. So first thing we're going to do is we're going to represent the carbons as little bumps, and we're going to hide the hydrogens that are connected to the carbons. So first we're going to connect this carbon to this carbon, so we make a single bond. When this carbon and this carbon connect, it's actually a double bond, so we show that there. Then the carbon to carbon single bond, carbon to carbon double bond, carbon to carbon single bond, carbon to carbon double bond. So now we have this structure. Next, we're going to do the carbon to carbon, carbon to the double bond oxygen, carbon to the oxygen, and then oxygen to the hydrogen. Because it is not a carbon to hydrogen, you need to represent that hydrogen. Now another thing to note is you do not need to show lone pairs, so you don't need to do that. So roughly drawing this, and this is what we have so far. Now next, we're going to have carbon to this oxygen, oxygen to this carbon, then we have a double bonded oxygen, then we have a carbon right here. Oops. Shouldn't put that C. So we're going to draw this out. So line to the oxygen, then we have the bump to the double bonded oxygen. So remember, where these little bumps are represents the carbons that are there, and then you just need to fill in the hydrogens. So this again is how aspirin looks like. Now, if you're curious about the naming of molecular formulas and the trends we use, we always first put carbon, then hydrogen, then any other atom in alphabetic order. So now we're going to go over Chapter 3, limiting reagents. And this is, again, a review because you learned this in Chem 200. So let's start with an example. Alright, so if I have ammonia plus hydrochloric acid makes ammonium plus a chlorine ion, and I was given 1 gram of ammonia, 1 gram of hydrochloric acid, how many grams of ammonium will I have? Well, first thing you want to realize is, well, I have 2 different masses for the reactant going into one product. I need to figure out which one's limiting. So the first thing I'm going to do is I'm going to convert the 1 gram of ammonia into the moles of ammonium. I'm going to do the same with the 1 gram of hydrochloric acid and convert it into moles of ammonium to figure out which one's limiting. So after working out the calculations, I figure out that the hydrochloric acid is limiting. So just to remind you about conversions, when you want to go from grams to moles, you're going to be using the molar mass, grams over moles. You find this from the periodic table. From volume to moles, you're going to use the molarity, moles over liters. Now for both of these, you can go back and forth. You can go from moles to grams, grams to moles, moles to volume, volume to moles, and vice versa. So now we're going to take this moles of NH4 plus, and now we're going to find out how many grams we have. So I'm going to go on the next page and calculate that out. After working out the problem, going from moles to grams using molar mass, I get 0.493 grams of ammonia. Now we're going to move on to chapter 17, equilibrium. So when we're talking about equilibrium, one thing we need to discuss is why all the reactions don't go to completion. Well, there are more than one type of reactions that take place. There's the equilibrium consideration and the kinetics consideration. So let's take a look at the equilibrium considerations. Well, the equilibrium optimal balance of reactants and products is determined by thermodynamic properties of reactant and products. While for kinetic consideration, we're looking at the rates or speed of the chemical reactions and is determined by the reaction mechanism. So when we look at the equilibrium final state, it's the optimum balance between the reactant and products for a given reaction and temperature. So if we're given an equation, for example the one here, we would want to put it into an expression or a reactant quotient, which is symbolized by Q. And what we notice is we put the products all over the reactants. Now one thing you want to keep in mind is that the big letters are concentrational. That means they are in molarity. So either the big M or the moles over liter. Now there is a difference between the reaction quotient and K. So Q has different names. It's known as the mass action expression, the concentration fraction, or the reactant quotient. More commonly, it's the reaction quotient. Well, at equilibrium, Q is equal to K, which is known as the equilibrium consideration. For this course, we are normally in the equilibrium condition. Now, K is known as the equilibrium constant. It is very much temperature dependent. So if we have Q, our reaction quotient, is larger than our equilibrium constant, the reverse reaction is favored. The reaction moves from right to left, forming more reactants until the equilibrium is established. Now, if our reactant quotient was less than our equilibrium constant, the forward reaction is favored. The reaction moves from left to right, forming more products until the equilibrium is established. Now a little bit more about K. K cannot be less than 0. So at equilibrium, either the products is more than the reactants, that means the equilibrium constant is more than 1, or the products are less than the reactant, meaning the equilibrium constant is greater than 1. So let's look at a few examples. Alright, given methane plus 4 fluorines goes into carbon tetrafluoride plus hydrofluoric acid. We're going to put this into a reactant quotient. So remember, our Q is equal to our products all over our reactants. So we're going to take CF4 and hydrogen fluoride. Now this coefficient right here is going to be subscript. I'm going to put it right up there. All over our reactants, so we have methane goes into F2, and again we have a coefficient, so goes right there. So remember, as the reaction proceeds towards equilibrium, the concentration changes. Q changes. At equilibrium, concentrations become constant. So Q becomes constant, and that's why it equals to K. Now let's take a look at another example. Now we have silver chloride goes into silver and chlorine ions. Now one thing you need to know about Q and K when you're putting it into an equilibrium constant is solids and pure liquids do not appear in Q, in our equilibrium constant. So when we write this out, our Q is going to equal to our products first. So we're going to write out Ag plus Cl negative all over, and because silver chloride is a solid, well, we don't have a reactant, so this is all we have. So let's show another example of this. Alright, we're given ammonia with water makes ammonium and hydroxide. So let's write out the Q. So first we're going to take our reactant, our products, so ammonium, hydroxide, all over our reactants. But one thing we need to stop for is this water. It's our solvent, and it's also in a pure liquid. So we will not see this in our reaction quotient. So let's fill in our last part. So this is our reactant quotient for this equation. Alright, so for your assignment, I want you to read chapter 17, sections 1 through 2. Your problems you're going to work on is 12, 18, 23, 33, 35, and 37. With number 35 and number 37, just remember Kc equals Kp. That C stands for concentration, P stands for pressure. Since we're only looking at concentrations, those problems 35 and 37 are great problems, but they do deal with pressure. So we're just going to go Kp equals Kc, and you'll get the problems.